I'm going to be covering topics in heat transfer, specifically the cylindrical and spherical coordinate system. So I'm just going to get straight into it. But before we do an actual problem, I'm going to do like a conceptual type of problem. So I'll just start. So let's say that this is right here is a cylinder, and you have heat. This is heat right here, like flowing all throughout. And this coordinate system is going to be the radius and the z direction, and then there's also going to be a phi angle. So this is for cylinder, so the coordinate system for that is as follows. Let me just write it really quick. You can skip ahead if you want. Okay, so this derivative represents the radius direction going along the radius, so going up basically. The phi is at an angle, and the z direction goes along the length of whatever tube you have. The q dot represents your heat gen. And this depends on time. So let's say we had some assumptions. Where for this one, let's say that it was two-dimensional. Okay, well, based on the heat that's flowing through, yeah, this is where heat's generating from. Oh, shoot. So you have two components in the heat itself. So this one has a horizontal component in the z direction, and this one has a vertical component in the r. So that means it's 2D in r and z. And also, let's say that it is steady state. So whenever you have a steady state assumption, the derivative that has to do with time is going to cancel out. So that goes to 0. This goes to 0. Secondly, the direction that is not used in this problem is this derivative that has the phi angle. So this also goes to 0. So you're only left with 3 terms of the radius direction, the z direction, and then your heat gen. So that's the fundamental of the coordinate system. So now let's do an actual problem. So I'm just going to sketch it really quick. You can skip ahead if you want. Where KT is going to be a thermal conductivity of some metal, and Kg will be another. Actually, let's keep it arbitrary with no numbers. But let's say you were given KT, Kg. Let's say you were given ambient temperature. Let's say you were given heat transfer coefficient, and also volumetric heat rate. Okay, and then let's say we're also given R1, R2, and R3. Where this is R1, this is R2, and this is R3. So in this problem, let's say you were wanting to find the following of temperature at the second radius, a function of temperature, and the maximum temperature. So finding these three. So first thing to do, also the heat gen, let's say that it is formed inside of this second region right here. That's where the heat is generating. Okay, so first thing to do is make a thermal resistance network. So this is going to be where temperature 1 is, temperature 2, temperature 3, and then your T infinity in the ambient air, as well as the heat transfer coefficient. So your thermal resistance network is going to start from the first temperature node. So at T1, you have thermal resistance in between T2, and this thermal resistance is for conduction. If you're not familiar with making thermal resistance networks, just let me know. I'll make a separate video explaining those. But so this is going to be resistance 1 of conduction, and then between temperature 2 and temperature 3 is another conduction, and then the resistance between temperature 3 and the ambient air is going to be convection. Okay. An important thing to note is wherever your heat gen is happening, you cannot include the thermal resistance. So between T1 and T2 is where our heat gen is generating. So we have to not include temperature 1. So this is our thermal resistance network. Now, an equation for using the thermal resistance network is Q equal to difference in temperature divided by the total resistance, R total. So if we're trying to find T2 and one of the givens is T infinity, then we can do Q equal to T2 minus T infinity divided by R2 conduction plus the convective thermal resistance. And R2 conduction is, for conduction, thermal resistance is L over Ka, and this K is between R2 and R3. So this is the Kg. And then for convection, it's 1 over Ha. Okay, well, one thing is we're not given heat rate. We're given the volumetric heat rate. So the Q triple prime, it has the units of watt per meter cubed, but our heat rate is just in watts. So we would need to we need to multiply by the volume of a cylinder. This one is going to be cylindrical. So volume of a cylinder is going to be 4 pi, and then the heat rate at which this happens is in between R1 and R2. So we have to do R2 squared minus R1 squared, and then L. This right here is our volume. So our heat rate is going to be the Q triple prime times volume. So whenever we substitute, or let's first solve for T2, like make an expression. So we're going to multiply this term over here. So we'll have the Q and then R2 conduction plus R convection, and then plus T infinity. So whenever we substitute everything in, T2 will be the Q triple prime F times 4 pi R2 squared minus R1 squared L, and then the two thermal resistances. So multiplying L over kGA plus 1 over HA, and then plus T infinity. And area of a cylinder, area that you are going to substitute into here, is going to be 2 pi R L. 2 pi RL, and the R that you use is R3, because that's where the convection is happening. And for the conduction, you would use the R2. Actually, I made a mistake. Right here, this is the conduction for thermal resistance that I used was for Cartesian coordinates, but for cylindrical coordinates, it's actually ln of R2 over R1 divided by 2 pi, and then the thermal conductivity, so that would be for KT. No, this would be R3 over R2, and this would be KGL there. And then when you put this in, the L's will cancel. They'll all cancel. Okay, so this would be the first portion of your problem. So that finds temperature 2. Now we need to find an expression T of R. So that's where we use the coordinate system. It should be on an equation sheet. It was the previous one that we wrote. I'll just write it again. And the assumptions that are going to be used. So we're going to say that it's 1D. We're also going to say that it's steady state, constant properties, okay, and there is heat gen. Okay, so based on that, if it's 1D, this diagram that we're looking at is the radius basically. So it's only traveling in the R direction. So that means we can cancel out the phi, and we can cancel out the z direction. And since it's steady state, we're going to cancel out the dt over dt. So we're left with the equation of, also, constant properties means that we can take this k variable to the outside of the derivative because it's not in relation to the independent variable of this lambda t over lambda r. So the equation we end up with is k over r, and then lambda over lambda r, and then lambda t over lambda r, plus the q dot, which is our q triple prime, times volume. Or for simplicity, you can just write q dot for now. You can just keep it as this variable. So now, to make this t of r equation, we're going to start by making sure that there's nothing in front of this partial derivative right here. So we're going to multiply everything by r over k to cancel this out. And so we'll have lambda over lambda r, and then dt over lambda t over lambda r. And then we're also going to move this the heat gen to the other side. Now we have this. Now, to cancel out this partial derivative, we'll do the integral of both sides. And this cancels. We have r lambda t over lambda r equal to negative q dot over k, and then integral of r. This is going to turn into okay. So our equation that we have is this. Now we need to divide r on both sides to isolate this derivative right here. So let's do that. Now we have this, and next we'll just do an integral one more time, and that gives us a t of r equation, and we're just going to do another integration. There should be an r right here, and this is going to give negative heat gen over, or times r squared over 4k plus c1 ln of r plus c2. Okay, and now we're about halfway done, but now we need to implement some boundary conditions. So for the boundary conditions, since we're using a cylinder that has heat gen at radius 1, we're going to say that for R equal to R1, that the change in temperature with respect to the radius at R equal to R1 is equal to 0. This is saying that since heat gen is generating at R1, there is a 0 change in temperature at that radius. And for the second boundary condition, we're going to say that R is equal to R2. So that is going to mean that T is equal to T2. And this T2 is what we solved for in the first part. So to use these boundary conditions, we can actually go back to this equation right here to solve for C1. So this dt over dr is going to go to 0. So we're going to say that 0 is equal to negative heat gen R1 squared over 2k plus C1, because we're substituting in R1 for everywhere there's an R, and now we're going to solve for C1. So C1 is just equal to the positive of this expression. And now we use this C1, and we're going to substitute it into this right here, where it's paired up with the natural log. And now we're going to use this T of R equation to solve for C2. So I'm going to replace this T of R with T2. So when I'm implementing the boundary condition, I'm going to say that T2 is equal to negative heat gen R2 squared over 4k plus C1 was Q dot R1 squared over 2k ln of R2, and then plus C2, and now we're solving for C2. Everything else is a known variable, so we just have to isolate this C2. So that means C2 is equal to T2 plus Q dot R2 squared over 4k minus Q dot R1 squared over 2k ln of R2, and that's what C2 is equal to. So now we're going to substitute in C2 into the general equation of T of R. So that means T of R is going to come down to Q dot negative Q dot times R squared over 4k plus C1, which is the Q dot R1 squared over 2k ln of R plus C2, which is all of this, so plus T2 plus Q dot R2 squared over 4k minus Q dot R1 squared over 2k ln of R2. And we could simplify this a little bit to just clean it up. So we can combine all of the Q dot over 4k variables, and then this left the R2 squared minus R squared, where this is where we substitute in any R value that we want to solve for a temperature at that radius. So we simplified this one and this one. So now let's simplify the Q dot over 2k. So plus Q dot over 2k R1 squared. Yeah, all of it's R1 squared. And then you can combine the natural logs. Since this one is negative right here, we're going to divide the radius by this R2. And then finally plus T2. So this right here is your T of R equation for this problem. So that's the second answer. And now to find the maximum maximum temperature, we're going to use this equation and we're going to set another boundary condition. So for maximum temperature, we're going to say that at R equals to R1, well, where would the maximum temperature be? That's going to be wherever the heat gen is happening, because that's where it's going to always be the hottest. It's not going to ever cool down. Well, it's cooling, but it's always generating again. So for R equal to R1, T is going to be equal to the T max. That's what we're trying to find. So we're going to substitute in T max into here. So let's do that. So T max is equal to, and everywhere where you see just a regular R, we're going to substitute with R1. So let me just do that real quick and see if we get the same thing. You can try and do it yourself. Okay. So that was for cylindrical, and now we can do one that is spherical, and the main difference is going to be A, the coordinate system that you start with, and B, the thermal resistances that are going to be used in the problem. So let's do that. So I'm just going to move over to the side here, and let's see. So for this one, let's start with the problem. So this is going to be this inside right here is going to be where the heat gen is going to be. So this is also R1, R2, and R3. Okay. And this is T1, T2, and T3. And also T infinity. So we're going to just do the same type of thing, but we'll keep it arbitrary. We're going to say what would be given to solve a problem like this. So we would be given T infinity, R1, R2, and R3. We would also be given let's just call this region K1 and K2, just for simplicity, but it would be just a material, type of material. And we're also being given Q dot, which is in the units of watt per meter cubed. So again, we're going to have to multiply by volume of a sphere this time. So let me just put that on top. If this is a sphere, volume of a sphere is going to be 4/3 pi r cubed. Okay. And also, we're going to be given the heat transfer coefficient for the ambient temperature, for the ambient air. So, we're going to start this the same exact way, where from T1 to T2, we're going to have this resistance. And then from T2 to T3, we have this. And then from T3 to T infinity, we have this resistance right here. So to draw that a little more neat, we'll have T1, T2, T3, and T infinity. And unlike the last problem, the heat gen is happening all inside of radius 1. So this is like the center, I guess. So the heat gen's happening all in this region, so we can't use that region. So that's why we start at T1 this time. So between T1 and T2, we have just R1, we could say, conduction, and then R2, conduction. And then between T3 and T infinity, we have the R, convection. So in this problem, we're going to be solving for, let's say we're trying to find T1, T of R, and again, let's try and find the maximum temperature. This is normally what would be asked for these types of problems. So R1, conduction, and R2, conduction. Let's just list them here so we don't have to rewrite them. If your exam is without a calculator, that most likely means you're just going to keep everything as a variable, and to save some time, you can just write the variable one time and not write it again. That way, you're not wasting space or time. So this is the equation for thermal resistance for conduction for a spherical coordinate system. Could probably move that. And then for the second one, okay. And then for the third one, it's convection. Let me just write convection. This is 1 over HA, where the area is the surface area of the sphere. So 1 over H times 4 pi and then R squared. And this radius is going to be radius 3. Because of the convection is only affecting the outer radius, which is radius 3. Okay. Now, same thing with our Q. We don't have Q, but we can make it with the Q dot that we were given times the volume. So volume we already wrote over here. This should be R3. No, this should be R1. R1 because the heat gen is happening inside of the sphere. So let me just write that. So Q is going to be our Q dot. It should be a numerical value times 4 over 3 pi R1 cubed. Okay, now we can use this thermal resistance network to solve for T1. So we have T infinity, so we have to use T infinity in this equation. So it's going to be Q equal to T1 minus T infinity. We already wrote all of the thermal resistances over here, so we don't have to rewrite them. We'll just write their variables. And you could even write that all of these is equal to R total. That way when you solve for T1 algebraically, it's going to be Q times R total, and then plus T infinity. And this will be T1. And that's part A. Now for part B, making the T of R equation, it's going to be using the coordinate system once again. So I'm going to write that really quick, and you can skip ahead if you want to the next part. Okay, so the same assumptions we're going to be using of 1D, steady state, constant properties, and there's heat gen. So that means we're going to cancel out the phi direction and the theta direction, as well as the time. So that means our equation is going to be k over r squared, lambda over lambda r squared, lambda t over lambda r, and then plus q dot equal to 0. Okay, so now I'm just going to do what we did last problem. We're going to bring the coefficient in front of this partial derivative being equal to 1. And also move the heat rate or heat gen on the other side. And now we can integrate, and we're going to have r squared lambda t over lambda r equal to negative q dot r cubed over 3k plus c1. And now we divide by r squared, and we get lambda t over lambda r equal to negative q dot r over 3k plus c1 over r squared. And now we can integrate. Now we have t of r equal to negative q dot r squared over 6k minus c1 over r plus c2. Okay, now up until this point, we're going to do the same thing by applying boundary conditions. So, since the heat gen is happening at the center, the very center, we can say that R is approximately 0. That's whenever the change in temperature with respect to the radius at R equals 0 is equal to 0. And then at R equal to R1, that's when T is equal to T1. So now, same thing as last problem. We're going to use this expression to solve for C1. Okay. So R is going to be 0 and dt over dr is 0. So that means 0 is equal to 0 plus C1. So C1 is equal to 0. So we don't have a C1. So now we need to solve for C2. So this term can go away. So we're going to replace T1 into the T of R equation right here. So T1 equal to negative Q dot R1 squared over 6k plus C2. And now we solve for C2. And so that's going to be T1 plus Q dot R1 squared over 6k. Now we substitute that back into the T of R equation. So T of R is equal to negative Q dot R squared over 6K plus T1 plus Q dot R1 squared over 6K. And now we can kind of simplify this by grouping together the Q dot over 6K variable, and we'll have R1 squared minus R squared. Alright. Okay, so that's your T of R. Now, to find maximum temperature, we're going to do a boundary condition once again. And the maximum temperature is going to be at the very center. So R equal to 0, that's when T is equal to T max. So T max is going to be Q dot over 6K, and then R1 squared, and then we're substituting in 0 for R, so that just goes away. And this is our T max expression. So that was for cylindrical and spherical. Those are going to be probably some of the hardest problems you'll see. I'll also do an example of a single fin. Yeah, so feel free to rewatch those segments if I went too fast. So this next example is going to be a single fin mounted on a wall, and it has a certain temperature at the base. It has a certain diameter and also a length. I'm going to keep it arbitrary once again. Okay, so some things that it may ask to find is the efficiency of the fin, the heat rate, and the effectiveness. So let's start with the efficiency of the fin. So if this fin is adiabatic, that means on your formula sheet there's going to be an expression for efficiency. So that's going to be the hyperbolic tangent, and then m characteristic length, and then m characteristic length. So this m variable comes from your equation sheet. For a cylinder, it should be on the very bottom. It says 4h over kd, and your characteristic length is going to be L plus diameter over 4. This is also in your equation sheet. If you have another shape like a rectangle, these will be slightly different, but they're still on the equation sheet in the same section. So you substitute these into this equation, and that should be your answer. That's all there is to it for that. Now for your heat rate, you're going to make a thermal resistance network. So starting from the base temperature, we have a thermal resistance of conduction, and then we have a resistance of the fin, thermal resistance of a fin, and then with adiabatic assumption, the tip is going to be equivalent to that of the ambient temperature. So for the heat rate, we're going to say that Q is being equal to TB minus T infinity over. So for conduction, it'll be L over Ka plus the thermal resistance for a fin is going to be similar to convection, except you're multiplying the efficiency of the fin with area of the fin times the heat transfer coefficient. Area of a fin, this should be included on your equation sheet. Okay. And then also your convection, 1 over HA. So that's the second portion. Now for part C is the effectiveness. So this is going to be equal to heat of the fin divided by the ideal heat. This is without a fin. So this is the same thing as writing this. And AB right here is the cross-section area of your fin. So if you notice, the temperature difference cancels, the H cancels. So for effectiveness, you're left with the efficiency times area of a fin times the cross-section area. Okay. And yeah, that would be part C, and that would be this problem. That's all I'll cover for now, but for later chapters, I'll try to cover those sometime soon. So yeah, good luck, and I'll see you next time.